Okay, so welcome to the Natural Hazards Research College webinar. Just a reminder of why we're here. Reduce disaster risk for the poor in tomorrow's cities. The Natural Hazards Research College remit has several elements. One is to improve the student experience in research underpinning these goals, and cohort building, so to kind of build a community practice of research in support of these goals, understanding in natural hazards and doing something about them. Developing international learning from local learning, sharing experience, to provide quality control on the activity and the outputs at an international standard. Capacity building in the host countries, to ensure a project legacy, and to provide an intellectual resource to support the city goals. So common to all of the colleges, it will focus on delivery. There's a number of things that we're going to do to achieve this these goals. One is the seminar today, but this is just the first of 4 for natural hazards. Mapping the resources available. You'll hear today about what kind of data might be available in Kathmandu, for example. Developing mechanisms for capacity strengthening and legacy development in the cities. We're going to, again, you'll hear a bit more about this today. We're going to use scenario building as a common thread, targeting the main obvious risks. We'll be looking at identifying training needs, engaging with interdisciplinarity. There are several research colleges we want to work with them, as well as working with the cities. We're going to be doing much of the work. Balancing detailed, intensive local studies with extensive analysis across different platforms and disciplines and countries. To do that, we want to engage with all the 4 city leads and build bridges between the relevant participants, access to relevant data. And also, because this project doesn't have all of the program set in stone, we'll be looking at developing new research questions that emerge from the work program and support the project goals. So this is the first of 4 seminars you'll all have heard about. The first one on earthquakes. We're going to be looking at floods. Next week, landslides and fire, on a kind of 1-week running program, and that's embedded into a wider program of Research College webinar that's already well established now. So we hope you tune into these as well and carry on with the program. I just said a few words. I'm going to introduce John McCluskey now, and then we'll go into the 3 scheduled presentations that Dave has already outlined. So over to you, John.
Hi, everybody. I think probably most of you know that I'm a seismologist in a previous life. So I couldn't resist saying a couple of words at the beginning of this presentation. This is, for me, I really applaud the dedication of the seismology team in moving from the things they normally do to developing a really detailed plan that serves the purposes of tomorrow's cities. I think if, for all of us, one of the things we can really learn of the way this has been done is the way all the methods and techniques that have been used have been carefully selected from a whole range of possibilities, including ones that we are more expert on, to develop a methodology that is specifically tailored towards the work of tomorrow's cities, particularly in looking at very high resolution at small scales. I'm looking forward for everybody to see this work. We've had some technical problems. Mark Naylor couldn't make it, unfortunately, to be here today for personal reasons. He's kindly recorded an insert into the talk, so it's a talk being given by 3 people. And Mark's unfortunately spoke over his time a bit, and we've edited a bit out of the center, which Deepak will cover later on. So I'll commend the talk to you, particularly about the way in which the seismology team has really worked to develop techniques fitting the Tomorrow Cities message. And I'll hand over to Karim to begin the formal presentation. Thanks.
Thanks, John. I'll share my screen, and can you guys see my presentation?
Yes, if you put it on full screen. Yeah, good. Okay.
Thanks, John, for the first section of the webinar. Thanks, Ian, as well. I will jump into the presentation. The idea is to understand how the hazard and risk interact with each other for the poor in the developing countries, but the methodology is the one that I will present, and then we will go back. We'll go to Mark's and Deepak's presentation, and then I will come back at the end to show some implementations, some example applications of the methodology. If we think about the seismic hazard, we are dealing with two main computational components. First one is the earthquake source model, which entails identifying the sources where the earthquakes can happen and the characteristics of them. And the second component is the ground motion model, where we quantify the effect of rupture on the built environment using the ground motion models. Different approaches can be used for this ground motion modeling. The conventional approach that is usually used in practice and in research is the empirical ground motion modeling, where you collect the recorded ground motion, and then you try to fit a statistical model through these data, which will give you the model that you can see here. If you are dealing with the seismic hazard analysis for locations that you have scarcity of data and instrumentation, you basically have no other choice but to go and use the ground motion models that are fitted for other regions and just use them by assuming the fact that they're going to work. Aside from this limitation, the main limitation of the conventional approach is that even though the number of ground motions that are recorded has increased in the past few decades, and the complexity of these ground motion models has increased significantly, the standard deviation or the uncertainty or variability that is implied by these models hasn't decreased. And you can see that the standard deviation of the example ground motion intensity measure here from 70s to 2010 and then beyond this, the range of uncertainty that is that you can obtain from these empirical ground motion models is more or less the same. The alternative approach that specifically is the point of interest for Tomorrow City is the physics-based simulation approach, in which, as you can see in this illustration, you specifically, and using the physics tools, let's say, you are basically modeling the source, wave propagation properties, and site response, and you try to rigorously address the underlying uncertainties regarding each of these components. This provides us with the way to scrutinize the uncertainties more rigorously. And it's the approach that is taking in the Tomorrow Cities in order to help the decision-making process for reducing the risk. This type of modeling requires three types of inputs. Let's say, first one is the earthquake source, where we describe the rupture that is happening, and the other one is the velocity structure of the of that part of the earth that we are interested to assess the risk for that, and we use various methods, and you will see the description of those methods by Mark in the next presentation, to understand the different layers of the earth that are contributing significantly to the ground motion and then the destruction of the structures on the surface. And the third component is the near surface soil properties, with the same importance that I mentioned for velocity structure. Historically, this type of rigorous high resolution approach has been utilized only in two main parts of the world: Southern California and currently Central California has been the pioneering of pioneering point for this approach. This approach is usually referred to as cybershake, and the second country is New Zealand. But you can imagine what the resources they have and what kind of accessibility to various things, including supercomputers and instrumentation and other things they have, compared to the countries or the cities that are the focus of tomorrow's cities. So this type of approach that has been taken in tomorrow's cities to address the hazard and risk in the poor countries, let's say for the poor in the developing countries, has been in the cutting edge of the research, and we are basically proud of utilizing this methodology for addressing the risk for the chosen cities. If we go back to the underlying concept of seismic hazard analysis, you can adopt two types of approach. One is the scenario-based approach, in which you are modeling the earthquake process and the propagation and other factors that are affecting the seismic hazard rigorously, and you end up with the field of ground motion that you can use to assess what will happen to your infrastructure. The second approach is the probabilistic approach, which is appropriate if you are trying to do the hazard analysis for a larger scale utilizing simplified ground motion models. Arguably, you can use physics-based simulation probabilistic approach, which is the point of cybershake in New Zealand, for example, and also in California, but that approach needs to be developed further. In terms of scenario-based hazard assessment, which is the methodology adopted in the hub, we need to look at this from the perspective of risk assessment, in which you have an interplay of these four different components. And when we are choosing scenarios to simulate and assess the impact on economical and social impact, we are basically considering the different perturbation of various parameters that are contributing to these four different aspects of the hazard and risk. If we go to an example of Nepal, if the first step of this is to select scenarios, and for that we go to the seismology and our understanding of geology of the region and try to see where earthquakes can happen and what types of, let's say, what magnitude, what intensity of earthquakes are possible to occur. Then by utilizing physics-based simulation, as I mentioned, we are looking to model the physics of the process and the propagation by by basically modeling these factors in the earthquake process. And we can propagate these scenario effects into exposure and then socioeconomical circumstances in order to identify the risk that is implied by these scenarios. I will talk about this example simulation for Kathmandu region. For example, for this simulation, which is an example of this type of methodology, we have chosen magnitude 6 event under Kathmandu Valley. This rupture is highly likely. It's very probable for this region. And the important point we want to emphasize is the fact that small and moderate magnitude ruptures are frequent for tectonically active regions, and the loss and the risk that is implied, both economic risk and social risk from this moderate to small magnitude ruptures, is very significant compared to focusing on major ruptures that may or may not, it might take a couple of hundreds of years to reoccur. I'm not trying to say that we wouldn't look into large magnitude ruptures. I'm trying to emphasize the fact that in addition to obvious large magnitude ruptures, we will actually address the small magnitude and moderate magnitude ruptures, and we will demonstrate how they will affect the risk and the loss in the urban environment. For this type of modeling or example, I just have simply utilized the 1D velocity model and very simple mesh of the topography plus the underlying, plus the deeper structures. But the point I'm trying to make here is that, for example, using this example, you might get two types of ground motions, that one is recorded on the outcropping rock, the other one is recorded in the basin. And you can see visually how different they are. If you want to get too detailed, this has the pulse-like motion induced by the soft sedimentary layer, and it's closer to the basin edge. Because of that, you see this type of properties here. We want to, what I'm trying to allude to is the fact that these properties of the Earth are very important for us for this type of approach. And because of that, we need to understand these deep layers and also shallow structure, shallow geotechnical layers with a good accuracy. Because of that, you will see Mark Needle's presentation talking about these factors. So hopefully you can hear this well. Please let me know if not. So
today I'm going to hopefully follow on nicely from Karim's presentation and talk about.
Okay, sorry.
Hello, and sorry I can't be here in person for the webinar, but today I'm going to hopefully follow on nicely from Karim's presentation and talk about the proposed work we're going to do with passive seismology in the Kathmandu Valley. This is work that's a close collaboration between Tribhuvan University, particularly Deepak, and Edinburgh University, with myself and a wider team in Edinburgh. First of all, because there might be non-experts in the audience, I want to give you a good conceptual model about what we're thinking about here. The problem we're looking at is somewhere where we might have a seismic source, which we can see here, an earthquake. The waves would propagate away from that earthquake, and then we have a basin, which would be like the Kathmandu Valley, and the seismic waves would move through the bedrock and then enter the basin and cause ground shaking in the local vicinity in the basin. And we want to understand from a seismic hazard, seismic risk perspective, what's the likely ground shaking that will be experienced in different regions throughout this basin. And there are these three elements to it. There's understanding the likely earthquakes, the range of likely earthquakes that are going to impact on this basin. You need to understand how seismic waves will propagate through the hard bedrock, but you also need to understand how the seismic waves will behave when they enter the basin. And to do that, we need to understand a few things. We need to understand the geometry of the basin. In particular, we can see we've got this lower boundary between the bedrock and the sediments in the basin. And because there's a large velocity contrast across here into the sediments and the consolidated sediments, understanding this is very important. There's also then understanding the properties of the sediments within the basin. And from a site response perspective, understanding the properties of the sediments near the surface is really important for understanding how the ground will locally shake and what the impact of that will be on the various buildings. If you wanted an analogy to think about this, you could think of it a bit like if you drop a stone into a pond. That would be a bit like the seismic source. We're watching the ripples migrate out across the pond. That would be like the waves moving through the bedrock, and then where it gets towards the edges of the pond, it might start interfering with reflected waves off the edge, and there might be other effects going on. Somewhere we might want to understand, say, the interference between those waves. There are some differences in the physics because with water in a pond, the properties of the water are the same at all depths, and here the properties of the sediments in the basin will actually change with depth. Generally, the velocity is increasing with depth. We need to understand that velocity increase with depth to understand how these how the basin will respond. But if you're from a non-expert audience, that might give you a visual picture of what we're trying to understand here. So yeah, in this talk, we're mostly going to be talking about this part of the system, about the what's happening in the basin. And for us, we're going to be talking about how we can use passive seismology to understand and constrain some of the properties of this basin. So what's the aims of the passive seismology work? Well, here we're going to acquire information required for assessing seismic hazard in the Kakana region of Kathmandu. We want to identify not only the best guess of those properties, but also quantify the uncertainty so that we can understand how the uncertainty propagates through into predicted ground motions. And this uncertainty quantification is going to be a focus, key focus of the work the UK PhD students are going to do. We will discuss several ways in which passive seismology fits into the workflow of going from the source modelling through the propagation through the bedrock through to understanding the basin response. And we don't want to use approaches, we want to use approaches that can continue to be used independently of us beyond the project so that this work doesn't die when the project finishes. We think that this capacity building and legacy aspect is important in everything that we do. Similarly, we're building capacity within the Kathmandu team by procuring the seismometer equipment that's required to do this work, and that will remain in Kathmandu beyond the project. We believe this approach provides the best opportunity for ongoing impact and change. So, what is passive seismology? Just a quick introduction for those who don't know. Traditional seismology, you'd make a bang, you'd use a seismic source. It could be some dynamite, it could be a hammer blow, it could be an earthquake, and you would study the waves that propagated away from that known source. Passive seismology takes a different approach. It turns out that there's a lot of ambient noise in the earth going on all the time anyway, and so it was realising with the rise and the advent of faster computation that we can use computational methods of cross-correlation to extract the signal that you would have seen if you had a source and a receiver, just using receivers, because we can look for the similarity in the signals between two receivers that they hear as a consequence of this ambient noise, and use that to reconstruct some of the information that we're interested in. So this has been a great innovation. For this workflow, we're going to be interested here today primarily around two aspects: how we can contribute to understanding the 3D model for the velocity structure of the basin, and kind of a subset of that is understanding the basin topography, what happens at the bottom of the basin where it interfaces with the bedrock. And the reason this is kind of a subset of the 3D velocity is because we're most interested in that because it's a large velocity contrast between the sediments in the basin and the velocity of the bedrock underneath. For high resolution site response, this is where we really would want to understand the properties of the soil in the uppermost layer. We would maybe take a slightly different approach to what we're going to talk about today. We would look at maybe having a high density of seismic stations and doing work at that scale. For the moment, that work we're putting on hold because of COVID, because it requires a lot more logistical challenges in terms of deployment that maybe are not feasible at the moment. The work that we're going to talk about today can be done in multiple one-day deployments by a small team with just 4 seismometers. So we think that that work is a lot more viable to be going ahead in the near term. And there are other sort of options of things we could do, like we could do an active source survey or a variety of different things. Again, that would require a lot more logistical efforts than we believe are necessarily going to be possible in the near term. So we're going to focus on these two aspects, which can be done, as I say, by a small team on multiple one-day trips. One of the other reasons we're looking at passive seismology is once you've got the equipment, it's relatively cheap and quick to go out and collect more data and fill in gaps that you might have in your data coverage. The other thing that we need to know about is how the velocity of the sediments changes through the basin. And we can use a technique which is called surface wave dispersion to understand that. Now, I want to just give you a conceptual idea of what that is. The figure on the left here, the animation, shows a surface wave. This is a Rayleigh wave moving along the surface of the Earth. And these are the waves that tend to cause the most damaging ground shaking. And you can see here how the ground underneath the wave is also being deformed. It's not just an effect that you see at the surface. Now, the figure in the top right shows us that the shorter waves tend to penetrate a short distance into the Earth. So they feel the part of the Earth where the velocity is quite slow. The longer wavelength waves reach deeper down into the Earth, and so they feel the region where the velocities on average is a bit higher. And the longer wavelength waves reach down even further, and so they feel the even higher velocities deeper down in the Earth. And as a consequence of this, the short wavelength waves travel slowly, and the long wavelength waves travel faster. And we can use this property of understanding how the short, the medium, and the long wavelength waves propagate if we can record the speed of those. And this is what we refer to as dispersion. If we can see how the short wavelength waves move slowly, and the long wavelength waves move more quickly, we can use this information to recover how the velocity of the sediments is changing with depth inside the basin. And this is really helpful for us to constraining our wave simulations. This is like saying what happened if the velocity of, again going back to the analogy of dropping a stone into a pond. If you drop the stone into the pond and the speed at which the waves propagated changed with depth through the water, what would we expect to see? And so this is what we're recovering. So that's what we're going to be doing. And the way we do it is we need a minimum of 4 instruments that we can deploy in a triangular survey with one central instrument. And then we can move those 3 outer instruments around, keeping the central one in the same place. This is a good approach for the current conditions because it can be done quickly, it doesn't require a large deployment, done with a small team. Shubhavan's experienced in this method. At the same time, we can collect the H/V data, which is what we need to estimate the depths of the basin. That's what will be the method we'll be using for the first part of the work. It can be done on non-consecutive days, and logistically, it's very flexible. We think that that's good given the current COVID conditions. Once we have that data, we need to do some inversion to understand the velocity profile. The traditional way is to do 1D inversion. This means we try and work out what's the velocity profile under that point where we've done the survey. It's really about the central point. The good thing about this is it's quick and easy to do. Some of the downsides are that it ignores the it doesn't tell us much about how the basin's changing around it, and that can add in extra information for constraining the survey. And so here are some examples of what 1D inversions might look like with fixed number of flares. This is a very traditional approach. Some work that's being done at Edinburgh that's been done already is to look at how we can do 3D inversions. And this is a sort of a synthetic where there's some seismometers, they're the triangles, and this is a plan view map which shows we've got some 5 kilometre by 5 kilometre region, and in the middle we've got this anomaly. This is what it looks like in cross section. We've got some low velocity, maybe sediments, we've got some higher velocity region with an anomaly in the middle, and even a higher velocity region beneath that. And using the novel 3D inversion, you can see that we can recover a 3D picture that is fairly reasonably approximating what we had as the input. And with these Bayesian methods, we can not only recover the best guess, but we can recover the uncertainty about it. So you see there's a lot of uncertainty around some of these boundaries and the position of the interface, but we can see that we're doing a good job of recovering the properties in these regions. So we're going to look at how we might use some of these novel methods that are being developed in Edinburgh to improve what we're doing. As I mentioned earlier, there is the possibility of doing high resolution site response, and we had anticipated doing some of this work in Kathmandu to get high resolution VS30 maps. This is the key information about the surface velocity in the upper 30 meters that's needed to feed into the site response. This type of deployment would be challenging during COVID times, given the logistical requirements, so we're not going to be prioritising it during this first phase of work, and we'll reevaluate the viability of this at a later date. Similarly, there are other activities that we have discussed around active source surveys, but these are also on hold. So in summary, we currently have a lack of critical information in the Kakana region for traditional seismic hazard and physics-based wave simulations. So we'd have to make a lot of assumptions in assessing seismic hazard at the moment. With the passive seismology we can use this H/V method, which helps us get a better estimate of the depth of the basin, and we'll be integrating that with the results from the SAFE database to get a good picture there, and a sense of uncertainty in our knowledge about the depth of the basin. We're going to use surface wave dispersion to estimate the shear wave velocity structure through the basin. And this is important for both the best guesses as well as quantifying uncertainty. We want to ensure that the successes of this work can continue beyond the project, and we're actively working to make sure that the methods we use, whether they're novel innovation in terms of the inversion or other aspects, we want to make sure that they can carry on within Nepal beyond the end of the project. And the workflows that we're proposing here translate well to other cities on other basins. They could be other basins in Nepal. Equally, they could be basins in Keaton or or Turkey or other regions. So I hope that this talk meshes well with the other things that you are talking about today, and thank you very much for your time. Bye.
Okay, I hope it was clear in terms of Mark's voice. So the idea would be that utilizing Mark's approach, what the approaches Mark mentioned, we will try to understand these deep layers in order to feed them into the simulation that we will do. Now, I will hand over to Deepak, who will describe this type of application and methodologies in case of Nepal and Kathmandu. I should.
Thank you, Karim.
Yes, thanks. I need to stop sharing. I cannot find the button.
Top right-hand corner of your screen, Karim, is it? No.
Can't see that.
Karim, do you have is Deepak sharing his screen, or perhaps you have a slide you could leave loaded up whilst Deepak speaks?
I don't know if I have the latest version of Deepak's.
Okay, so if Deepak clicks on share screen, it should automatically switch to him.
Maybe I can leave the meeting and Deepak can.
No, don't do that.
Okay. Okay.
Deepak, try and see
Deepak is on now. Okay.
So can you see my screen?
No.
See your screen.
Yes, we can. Brilliant. Good.
Just a moment. I cannot see my screen. Let me share again. Can you see my screen?
No, the share button is on top right corner. You actually did share your screen once, but now we can't see your screen.
So I'll cancel it and do again. Oh. Cannot, right? It's a shared desktop.
You should see a button which is a rectangle with an arrow pointing into it that says
Yeah, I'm doing that. Yeah.
It worked a couple of minutes ago, Deepak. If that helps.
Maybe I can share. I have your version, few hours ago version of your presentation. I can share my screen and show you.
Oh, okay. Now I can. Can you see my screen?
Yes, we can.
Okay. Hi, namaste to everybody. I'm Deepak from Kathmandu. So, whatever in the previous presentations, as Karim and Mark Neller mentioned, that actually we need a precise basin model, 3D geological model for the 3D basin simulations. So for that, we are reviewing and collecting and integrating all the geological data as well as the subsurface data that were derived from the geophysical as well as other direct method like the drill hole data. And some of the important work has been done before in 1980, Moriabasi and Mario using the gravity method. And we have the geotechnical data from Cattell, and JICA has done very extensive work in Nepal, in particular in Kathmandu Valley in 1990, 2002, and 2018 for the subsurface geology. And similarly, the Podel et al. In 2013, they have done extensive passive seismology using a single point measurement. And Gilder et al. 2020, they have integrated all these database to propose the 3D basin model for the Kathmandu Valley. So in JICA in 1990, they have prepared the lithological database for, actually that was for the groundwater modeling for the Kathmandu Valley. And they have already a lot of database up to the bedrock, drill hole data up to the bedrock. In 2002, for the assessment of earthquake hazard, JICA produced extensive database and also some of the BS profile using the PS logging technique and shear wave velocity for the sediment. And recently, in 2018, they have gathered, integrated a lot of geolithological database to estimate the rock depth distribution. And they have prepared the several geological cross-section along east-west and north-south directions. In the 2018 database, they have used the different array microtremor result also, like L-shape 3-point array microtremor, and the triangular array microtremor also. And with using this database, they have come up with a very nice 3D basement, the basement topography of the valley. You can see here, this is almost the deepest part of the valley, this part, where the basement topography is around 763 to 800 meters, means here almost 600 meter thick basin sediments are here. And basically, within this project, we are focusing on the southeast part of the Kathmandu Valley, that is the Kokana region, somewhere here. And they have produced a lot of cross-section in east-west and north-south sections. You can see in this map here, this is our Kokana area, where there are limited database in terms of lithological drill hole data, as well as other passive seismic survey data. And this cross-section along line E, that means this section passes through our study area, the Kokana, which is shown here. So you can see the very uneven, undulated basement topography in Kathmandu Valley. So you can realize that how uneven the basin is actually. And after that, in 2018, Bijukse attempted to simulate the basin to develop the 3D profile of shear wave velocity in Kathmandu Valley. Actually, he has drawn some of the cross-section along this line. So you can see almost this section A line somewhere here. So that is the first in the topmost, this is the section through A dash. And you can see here the different layer of sediment with the characteristics shear wave velocity here. And from this study, they have found that the weathered bedrock is about 632 meters at the deepest part. And it ranges from, in the periphery side, and in the deeper part, it goes up to the 632 meters. And recently, this Gilder et al. In 2020, they have collected all this data and integrated to propose the integrated model of bedrock elevation in Kathmandu Valley. And they have produced using the lithological data and microtremor data and also the gravity data. So they have come up with almost the Y-shape value somewhere here. You can see the Y-shape value here. And with this one, so we can say this topography of this basement in Kathmandu Valley is quite uneven and is drastically changed from point to point. In 2013, the point micro tremor survey was carried out in Kathmandu, covering the most of the part of the urban area of Kathmandu Valley, and it was done by Powdell et al. In 2013. You can see the different microtremor measurement sites here. So they have carried out 172 single point measurement in Kathmandu Valley. And they have come up with the basement topography map for the Kathmandu Valley. You can see here, our proposed study area is Kokana here, somewhere here. And at the deeper part, in the central part of the valley, you can see the depth varies reaches up to the 300 meter, somewhere here. And they have come up with a 3D model of the basins. So you can see the single depressions at the central part of the Kathmandu Valley. So that depth range goes up to the 300 meter at the central part. And however, having all these passive seismology data, and if you compare with these all data with the direct observation through the drill hole, there are some discrepancy between these regions. So for example, in Powdell et al. Model, so they have estimated the depth at the borehole 1, so it's located somewhere here. They have estimated the depth to the bedrock is around 190 meters, somewhere like that. But the actual depth of the bedrock is around 250 meters. So there is a little bit discrepancy on this data. And similarly, in the PS2 also, they have estimated depth to the bedrock is around 190 meters, but actually it's more deeper than 260 meters. At the central part of the valley, you can see that is in the central part of the valley, that lithological data has estimated this bedrock is around 560 meters somewhere here. But the estimated depth using this passive seismology is around 200 meters. So we have this kind of discrepancy because of this. They have carried out the single point microtremor survey, and sometimes such techniques miss the long wavelength, and our estimation will not be accurate. And for this uncertainty reductions, so we are planning to carry out the array noise measurement, as Mark already mentioned that. So for the uncertainty reductions, we are taking reference of the borehole that raised up to the basement. So this red dot here, we can see these are the location of the borehole that has raised up to the bedrock. So taking this reference, we are planning to have the noise measurement nearby, or actually close to this point, so that we can cross-check or we can validate our result with the real litholog of the area, so that we can revise our model and prepare the very accurate model for the Kathmandu Valley. And for this, we have a plan. First of all, we are preparing the 3D basin model on the basis of existing geological and geophysical data, which is ongoing. And similarly, passive seismology, ambient noise measurement, we are planning here. There is a steady progress on the procurement due to the COVID-19. And similarly, we have a plan to deployment of accelerometer across the valley, so that we can use the future earthquake that we are going to measure to compare or to validate our 3D basin simulation results. And finally, having all this passive seismology data and other geological model, we will refine and validate our 3D basin model, integrating the geological and geophysical data. And physics-based 3D basin simulations we will carry out, and some of the preliminary model for simulation is in progress. And having all these simulation results, we will assess the seismic hazard in Kathmandu Valley and particularly in Kokana region. And after completing this work in Kathmandu Valley, we have a plan to move in the other basin of Nepal for the 3D simulations. And regarding the other basins in Nepal, so basically we have classified the basins of Nepal in two categories. One is intermountain basin, which are located in the Lesser Himalayan zone of Nepal. The Kathmandu itself is a intermountain basins. And other is the Pokhara, so which is rapidly urbanizing and is in high threat of the earthquake in Pokhara Basin. So we have a plan to carry out the similar study in the Pokhara Valley too. And the other side of valleys or basins are in Shivalik region, in the sedimented rock. So those basins are also called the Dune Valley, as they are located in the Shivalik region of Nepal. So these dune valleys are rapidly urbanizing these days because people from the mountainside are moving in this part of the valley. So because these valleys are very fertile, so we have a plan to carry out a similar study in Surkhet Valley, in the Western Nepal, Dang Valley, Deokhiri, Chitwan, and Hetauda. Thank you very much. Hello.
Sorry, can you guys hear me now? I was
Yes.
mute.
Yeah.
Sorry about that. I was mentioning the fact that Deepak and Mark mentioned described the main aspects of velocity structure and near surface modeling, which are the important parts of the physics-based simulation approach we have taken. Going back, and I will describe a little bit about the source modeling and so on, and I will show some example animations and implementation of this type of approach. Going back to the same example of simulating a magnitude 6 event in Kathmandu region under the valley around the depths of 10 kilometers. This is a typical kinematic rupture model that has been developed for this. The size of the rupture can be bigger than this one, but this figure right here shows the energy release in different patches of the sources, and you can think of summation of these values here will basically indicate the energy that is released during the rupture. As you can see, the rupture is happening in a finite fold, meaning that there are dimensions in depth and length. And if we assume the rupture starts at some point, and there is an uncertainty around where this point is, if we assume this is the point, the rupture evolves during some seconds from the hypocenter, from the rupture initiation point, in order to reach to the ends of the rupture, and then the waves propagates after that throughout the crust. If you look at the slip direction, different patches, different parts of this rupture, different parts of this fold ruptures in a certain direction. Collectively, they might be aligned in some directions, and these are different other parameters that are of interest, and they govern the slip properties, and hence they govern the properties of the ground motions that are recorded. But I wouldn't go deep into this. This is an animation of that rupture. So this rupture occurs at this point in the geological setting. Unfortunately, the animation is not really that high quality. It's just a preliminary animation. But what you can see here, once I play this, is you will see colors of red and blue. They describe the wave front, which is basically the front, the progressing end of the rupture, end of the waves that are propagating from a point towards different locations. And at this point, the rupture has been finished, but most of the waves are still traveling through the deep crust in order to reach to the surface. And you can see some motions now. And then as the time goes by, you will see that the motions, the waves are propagating throughout the crust to different regions. The importance of this approach is that if you are, for example, trying to assess the landslide in different parts of this region, or liquefaction or damage to different infrastructure, you can directly use these ground motions that are simulated and do the assessment for your system, either it's landslide or a bridge or a building. in order to show an application or an example application of this, and also in order to stress on the fact that deep structure and earth structure is really important, here's an example of the ground motion simulation that is utilized. This ground motion has been recorded, or let's say simulated, on the bedrock and the outcropping rock of the model you just saw. And what you can see is that there is a significant amplitude for this. Just for the technical reason, I'm just plotting the velocity here in order to see the pulse-like motion. However, the acceleration is applied at the base of this building. You can see there's a moderate movement of the building, and because the vibration period of this structure is close to 1 second, and this Fourier spectrum of this velocity waveform is away from that 1 second, there is not much amplification or resonance in the building. Whereas if we look at this, another ground motions from the same simulation, but is basically recorded or extracted from the response that is at the point that is above the basin with the soft sedimentary layers, you will see a clear distinction in the response of the building because of this pulse-like motion you can see here. And obviously, this type of responses can cause either very significant damages or collapse in the buildings. As you can see, these large movements at some point will cause collapse in the structure. And the simulation finishes here because of the fact that I have approximately assessed the fact that at this point, this structure will collapse, even though the numerical model that I've used, the simplified one that I've used, is not capable to represent that. In any case, this type of ground motion simulation, physics-based simulation, can be directly utilized in order to assess building infrastructure, landslide, liquefaction, and other aspects of the hazard. In terms of next step, Deepak mentioned a couple of next steps, and I will just try to reiterate on that. The aim is to understand the deeper structure of the Earth, then utilizing passive seismology, utilizing other data sources, then utilize physics-based simulation and our understanding and the cutting-edge understanding of source initiation and source propagation in order to simulate ground motion. At the end, the simulated ground motion will be used here in engineering and social risk assessment, because that is actually the big aim here in tomorrow's cities, to quantify the risk as much as we can due to the scenario events that could occur, and then use them or prepare them as the tools that decision makers can use to identify and also plan for the future events that might occur. This will be the end of, I guess, the presentations. So it would be nice to hear your comments and questions. I'll start sharing, I guess, or not, because I don't know how to stop.
Thanks, Kareem. So I think Kareem, Ian, John, and Deepak are going to be around to answer questions for anyone that is able to stay now. And for anyone that isn't able to stay on, I've just posted a feedback form in the chat, which I know you may well have filled in these at previous webinars, but we're assessing the feedback that we get and are using the feedback to design and plan webinars that best suit the needs of our audience. So please do fill them in, and we'll help deliver more webinars that you want to see. So unless Ian or John or Deepak have any final comments on the presentation, we will go to questions.
I'll just make one quick comment. We had to edit a bit out of Mark's presentation. We'll make sure that whole I thought his presentation was really excellent, so we'll make sure that all of that's available for people to look at who are particularly interested on the passive seismology.
Yeah, thanks, John. That's a really good point, and I'll make that available with the recording of this webinar. If we can move on to questions then, we have a question from Tom Randa from our Nairobi team. If you'd like to read your question out, Tom.
Yeah, thanks a lot. I think I have to commend the presenters for the detailed and more elaborate presentation on the ongoing works. My question, I think, was just a follow-up on how maybe projections in terms. I'm not an earthquake expert, but rather a flood risk modeler from Nairobi Risk Hub. And just from the general knowledge of modeling, I know that as you increase the timelines into the future, the uncertainty in modeling increases. How is that being taken care of following that the outputs of the models are intended to be used to influence policy and actions to increase resilience in terms of these disasters, and specifically for earthquake? Thanks.
Thanks. May I respond? I have something to say regarding that. I don't know if I should first reply.
I think it's best if you chair the responses from the team, Karim. So you lead on the answers. Good.
Okay. Since Mark is not available, it's up to Deepak and me to handle this. So I guess in terms of if I had understood your question well, in terms of the time, we are talking about when the time scale in which various types of events can happen. So different types of scenario, depending on the time scale, can happen frequently or they can happen rarely. And in terms of earthquake scenarios, the range that I've mentioned in terms of addressing the major events that they rarely happen, they have a recurrence interval around a few hundreds of years. We will address those types of events because we don't know if, God forbid, one of them will happen tomorrow or 100 years from now. The other thing is that we will also address the small events that are frequently happening in the next decade. Let's say a few of these magnitude 5s and 6s and so on will happen. If any of them are in urbanized areas, then there will be a significant destruction and disruption, at least for the businesses and the life of and people's lives. So in terms of the time scale, we would like to encompass the spectrum from the rare events up to very frequent events. It would be nice if I could stop sharing my screen to see the question. Dave, can you help me with that?
So what happens if you go into the share tray, Karim? Is there an option to stop sharing at that point?
I cannot see that share tray.
Dave, just carry on and read out the questions. That would be useful.
Okay, so the next question then is from David Rush. If you're still with us, David, you'd like to ask your question? One of your questions.
Only one of them, okay. Thank you very much for your talk. Obviously, earthquake is across the city. This is very much a Kathmandu focused presentation. So what are the differences between the hazards across the cities, and therefore would you change your approach in analyzing them because of the different hazard? Yeah, that's my question.
Okay. The question was, what if we have different properties to seismic hazard, or different properties to different hazards, basically?
Earthquake hazard. If you had different properties to it, would you go around? Would you analyze it would you fit your process to the type of earthquake hazard that you have?
Yeah. So the methodology itself is rigorous and very robust to handle any range of possible events from very small magnitudes and to the large magnitudes, and different conditions of the secondary effects in terms of if you have a different types of earth structure or sedimentary layers or basin structures or topography, the methodology as it is will be able to handle those situations. So in terms of the capabilities of the methodology, it's robust. It's mathematically speaking, it solves the differential equation of motion for the elements of Earth that are built in a numerical model. So that is, and it's capable to handle various physical properties. So in terms of that, we wouldn't change the methodology. It is capable of encompassing different ranges of the hazard. In terms of computational effort, for example, the Istanbul case, the topography is not a major issue for Istanbul. The land surface is not very, let's call it, topographically wild. But if you go to case of Istanbul, which I encountered in an example case that I was preparing for this, there is a Mount Everest in the northeast corner, 8,800 meters, so above the Earth mean sea level, and you have very low land. We want to do the simulation for the whole Nepal, numerically doing the mesh for this, not doing the mesh, basically loading that into supercomputer in order to do simulation might be challenging, but this will not stop us from doing this. There are partitioning approaches. I'm becoming very technical. I don't know if that's appropriate, but there are partitioning algorithms in order to partition the mesh in a way that is optimized and it's capable to handle these difficulties. So speaking of little differences between the cities, there will be differences in terms of the techniques or approaches we will take, but in terms of methodological level, the methodology is capable to handle any seismic situation or, let's say, conditions.
Thanks, Kareem, and thank you, David, for your question. We'll come back to you for your other question if we have time later. Tanui, Ian Main, you have your hand up. Is that a further comment?
Yeah, just to come back to what David has asked, I mean, clearly there are fundamental differences between the hazards, and this is the Hazards Research College. But a lot of the commonality is in the methods of quantifying hazard and then transferring that to vulnerability and exposure through into risk. And that's what you need in order to make decisions, obviously. So we will be feeding some of that into you know, the mitigation of risk as a general theme for the whole project. But I do think there are maybe synergies in terms of quantifying hazard in a statistical sense. You know, things like the 100-year flood has an equivalent in the 100-year earthquake and so on. And there are maybe, you know, methods in statistical seismology that could be kind of, you know, kind of transferred along or from other subjects. So I would say that's maybe the main one that we can maybe look at in the short term. Not so much, obviously, things like ground wave motion propagation. That's not going to transfer too easily into some of the other hazards. But the general kind of how likely is an event is quite common, I think.
Thanks, Ian. Our next question is from Tanui Charles. If you'd like to ask your question.
Yes, excellent, David. Yeah, the presentation on the models are actually quite excellent, and being one of the policy analysts and impact champion under the Nairobi Risk Hub, the engagement so far, especially with the technocrats and the policymakers, is that gap between the evidence, especially from models to informing decision making, and from the experience from the earthquake study team. How often do you engage with the local communities, especially the urban poor and the policymakers at the city level? What is your experience when you share those kinds of models to inform some of their decisions and maybe the policy? And how did you structure or do the synthesis to generate the policy and some of the concrete lessons. Because we will be experiencing almost the same in Nairobi because of the two modelers also working on flood and fire, and we like to learn from you. Thank you.
I might be able to help with that, Karim, if you want.
Yes, please. And I was going to show this slide and say something, but I think.
No, go ahead. I just think it's a really, really excellent question, and it's a hub level question. Good. Go ahead, Karim.
So I'll say the little things that I know about this. So in terms of what really will impact people, although we are focused on seismology and the technical side and physics of the problem. At the end, as you can see here, and also referring to Carmine Galasso's presentation about the risk, we are doing these physical science and technical research in order to just come or get to the point of quantifying and illustrating the economic and social loss. And this is the part that can be useful and will be useful for policymakers. And the idea of we don't want to stay here and play with the physics of the problem and leave it there. Actually, the full spectrum of these steps that you are seeing here is the aim of the hub. And there are different colleges addressing these different problems, and I can refer comfortably to Risk College that Carmine also is leading. We are basically working closely in order to do whatever we want here in a way that is sensible and transferable to the economic and social impact side, which will delay with the economic loss plus the impact on people and the delays and so on. That's what I have to say. I don't know if that addresses some parts of your question.
Maybe if do you have a good case or of interaction, especially with the Apan poor, presenting such to them, and what are some of the feedbacks, especially from the Apan poor and the policymakers?
I personally don't. Maybe Deepak can mention something about this.
Yeah, actually, so our social group, social science group, also working on that. Actually, the risks we have in the Kathmandu Valley, especially in the coconut regions, that valley, as you know, this hit by many big earthquakes in the past. Since 1255, we have good records. So people are very much, aware about these things. Actually, they are seeking for the solutions. Actually, they want to know the level of risks they are in their places. So that is why the people, we do not have till now, the detailed interaction with the people, but some of the workshop we have done before, and the social scientists who are working on this, they may answer rightly. But in my view, the people have very good, the reflection about our work, and they are very eager to know the risks they are having in their area. So we have very positive feedback from the people on this work. So John, maybe you can add something on this.
Yeah, thanks, Deepak. I think you two have answered that question really well, but I just want to make a couple of extra comments. Charles, really good question and really important. This is the hub is about. What we need to do, and what I think the seismology team is doing, is developing a method that feeds into the decision-making process. And in the Kathmandu project, for example, and this is common to many of the cities, at this stage, some of the physical science is not engaging completely with the urban poor. So, for example, in Kathmandu, there is a work package which doesn't contain any physical science yet, which is engaging with the community in this area, Kokana, which is being developed. And the physical science at the minute is still slightly separate from that. And the plan is that these things will be united later in the research inception project, mainly through the concept of risk. So trying to bring these ideas of hazard through the ways in which we can describe and quantify risk. So your question is a really good one. Nairobi is taking a slightly different approach. In Kathmandu, at the early stages that we're at the minute, the flooding and earthquake teams are working separately, but with a clear strategy for integrating with the social science and governance type work packages later on. I hope that helps you to understand the strategy in the Kathmandu group. Istanbul is dealing with seismology slightly differently, and I think in the future we will probably consider this type of methodology. Some of the Quito team who are here might want to comment on this. In phase 2, we may think about using this type of seismology methodology in Quito. Charles, I hope that helps between the 3 people there.
Yes, that I look forward especially to interact and really experience that interaction between the 2 sciences and the APANPO and the policymakers. Thank you so much.
Can I, this is Carmina, can I make a comment as well?
Please do, Carmina.
Yes, so I mean, John and Karim and Deepak clearly say the link with the risk. I would say that there is also a great opportunity here on the work that Ian Stewart will do on communication, because what Karim showed in his final slide. So because I guess, Charles, your question is also about community directly, so not just policy makers and decision makers, but also really community. So I think those animations, for instance, that Karim has shown at the end, can really help a lot in understanding how to behave, for instance, during an earthquake or during a flood event. So I see some potential here also for the work on risk communication that again is led by Ian Stewart. So again, also use those type of model really for risk education and risk awareness within communities. And so say, if you expect this type of earthquake event, that will be as you live in this type of building, you expect this type of shake, what you should do. Should you just, run out? Should you drop, hold and drop, cover and hold on? And so also for this type of more direct work with communities. I don't know if John, you agree on that, and
sure.
That will also be.
Yeah, absolutely. Yeah.
So Charles, I hope that's useful as well.
Thanks, Carmina. So Daniel and Rade, you had your hand up. If you're still with us, let's check if you're still here. Danielle, can you hear us? You still have a question?
Yes, thank you. Sorry, Dave, who did you give the word to?
Yes, that's to you, Danielle. Thanks.
Thank you. A very quick question, just a technical information about the experiment that Mark Naylor was showing in his presentation. What kind of sensors are you using for this kind of experiment? What kind of seismic sensors? I would like to know that, and what is the minimum capabilities that these sensors should have in order to obtain the best results? Thank you.
I guess it would have been nice to have Mark to reply to this, but I wouldn't try to imitate Mark here. So I got no answer for this. I don't know if anyone on the call.
Deepak will definitely.
Yeah. Okay. So I have some comments on this. Okay. Basically, we are procuring, the seismometer for this one. So it's a broadband seismometer. So we are going to carry out the array type measurement. So the length of the array, it depends on the site, but it is better to have the longer array. So in our previous experience, we had done some measurement using 150 meter array, but being the dense settlement over there, so we should care about the size of the array for that one. So as you know, some of the data, geophysical data like gravity and some other study, it has shown that the depth of the sediment is about around 600 meters. So it is better to have the longer array as much as possible to capture the real properties of sediments as well as basement to get the realistic velocity model. So it is better to have the longer arrays based on the field size. So we will try to have as much as possible longer array for the noise measurement.
Could you
We are not
possibly
going to use the sensor, right? Actually, we are going to use the seismometer broadband.
Okay, could you make some comment about the frequency response? Maybe that's what Daniel's interested in.
Yeah, so actually from the previous study, the fundamental frequency for the Kathmandu Valley is around 3 Hz in Kathmandu Valley. So that is why we are trying to have the seismometer we are going to procure is, I think, is 0.003 Hz to more than 100 Hz, I guess. So that has the broad range to measure the noise in the area. Hello.
Thank you, Deepak. Is that, Danielle, does that answer your question, or does anyone else want to come in on that?
It's perfect, thank you.
Great. In that case, Chris Bean had a question. You had your hand up, Chris.
Thanks a lot. Yeah, thanks everybody for a nice suite of presentations. So I get this is more on the technical side. When I look at Mark's presentation, I guess it's a schematic, but he shows faults that are outside the basin, and I'm just wondering, Kareem, I guess the group's putting a lot of effort into defining the structure of the basin and its physical properties, but the location of the rupture will be really important in terms of, ground shaking. So for example, if you get a basin bounding fault or something in the basin ruptures or just below the basin, I think you get a lot of energy trapped in the basin relative to an event that's outside and it's not actually occurring within that structure. So I guess what I'm asking is, how much control do you have on the possible locations of the events themselves? I think that will be quite important in terms of the amount of energy it actually gets trapped in the basin itself. We've seen this for other types of scenarios where events that are outside these low velocity structures are nowhere near as shaking, if you like, as events that occur inside in the structure where all the energy gets trapped in there. So that's just my first point. I guess, Kareem, you're gonna look at that. The second point that I thought the Deepak's overview was really, really nice. And one of the things that struck me is, you've got these boreholes, and yet the microtremor, the lithology logs in them, and the microtremor depths don't always match the depths from the lithology. But I wonder, do you have any sonic logs in those holes? Is that discrepancy somehow related to a lack of velocity control? And if so, if you have the sonic logs been used, or if they don't exist, is it possible to run some sonics in some of those holes to try to constrain the velocity structure a little bit better, which would, and of course, help the estimate of the depth? Thank you.
Thanks a lot, Chris. It's very, very good point, and that's actually one of the main things that we will try to address in terms of both Nepal and Istanbul, both Kathmandu and Istanbul. But in terms of Kathmandu, it's more severe in a sense that the database for where the faults are not, let's call it, up to date, in a sense that we don't have much data. Geological maps and so on, they show us something, but what we have, what I at least have envisioned for this is to try to do the quote-unquote uncertainty propagation, in a sense that we would consider as much as we can all the scenarios that might occur inside the basin, in the edge, and outside of the basin, in the places that are even if they seem remotely possible, we will consider them for the simulation. We will have the database of simulated and propagate that to the risk side in order to have that answer in our hand in case we need to convey that message to the policymakers and so on. So to answer, long story short, my current understanding of Nepal's tectonic setting is very little because of the fact that I just started. I joined the Nepal team in 2 or 3 months ago. But your point is very important for the type of things we are doing. When we will certainly consider that. I will hand over to Deepak for the second part of your question.
Thanks, Karim.
Thank you.
Thank you for very good and important questions for the simulations. So far, the depth of the seismogenic fault in Kathmandu Valley is, this main Himalayan thrust, that is a plate boundary thrust between the Indian and the Eurasian plate. That is the main seismogenic fault for our region, actually. The depth to the seismogenic fault is around 12 or 15 kilometers, just below the basins. So we have that fault. So that is why we can take that data. We can start from that point. And also we have a lot of aftershock event after the 2015 Gorkha earthquake. So we have the proper depth from those events. So we can take a reference of those events as well as the depth to the seismogenic fault. So I think these two data can help us to constrain the depth to the rupture plane, I guess.
Okay, thank you.
Could I just, Chris, I think that's a really, really important point. The idea of seismic waves being trapped within the basin from an event that happens within the basin or a basin bounding fault. Deepak, do the earthquake catalogs, for example, the aftershocks to the Gorkha earthquake, are there any near surface events in that region?
Oh,
within the Kathmandu Basin, for example, or close to it?
Yeah, there are, I guess in my previous study, I think there are more than around 10 events. So that magnitude 5 within the Kathmandu basins. So we have, the tentative depth for those earthquakes. I think we can take those events as a reference to constrain the rupture depth to the rupture plane, I guess.
So I think that really, Karim, sets up a very interesting investigation. Some scenario earthquakes actually within the basin, of maybe using some of these 10.
Yeah.
Magnitude 5 earthquake within the basin could be quite destructive.
Yes, exactly.
Yeah. Good. Thanks. Thanks, Chris.
Thank you. Thanks, John. Thanks, Deepak and Karim.
Yes, thanks.
Great. So this webinar is scheduled to finish in 2 minutes. I can see we still have questions from Gakana and George. I might suggest if you could write your questions in the chat box, and if the presenters are able to continue the discussion, those questions will appear in the Teams channel. And if that's not right, then post them in the Teams channel once this meeting is ended, and those conversations will continue. And I think that way we will hopefully be able to give due kind of attention and response to your questions. So I'm going to post the feedback form for this webinar in the chat again. If anyone has a couple of minutes to fill that out, that would be greatly appreciated. And I would like to say a massive thank you to our presenters today. So to Ian, to Karim and Deepak. We will be back together next week for a flooding webinar at 2 o'clock next Thursday, and I'll send a registration form out for that tomorrow. So thank you very much for attending, everyone, and we will see you next week.